In the field of computer networking and other packet-switched telecommunication networks, the traffic engineering term quality of service (QoS) refers to resource reservation control mechanisms rather than the achieved service quality. Quality of service is the ability to provide different priority to different applications, users, or data flows, or to guarantee a certain level of performance to a data flow. For example, a required bitrate, delay, jitter, packet dropping probability, and/or bit error rate may be guaranteed. Quality of service guarantees are important if the network capacity is insufficient, especially for real-time streaming multimedia applications such as voice over IP, online games, and IPTV. Since these often require fixed bit rate and are delay sensitive, and in networks where the capacity is limited resources, for example in cellular data communication, in the absence of network congestion, QoS mechanisms are not required. A network or protocol that supports QoS may agree on a traffic contract with the application software and reserve capacity in the network nodes, for example during a session establishment phase. During the session, it may monitor the achieved level of performance, for example the data rate and delay, and dynamically control scheduling priorities in the network nodes. It may release the reserved capacity during a teardown phase. A best effort network or service does not support quality of service. An alternative to complex QoS control mechanisms is to provide high-quality communication over a best effort network by over-provisioning the capacity so that it is sufficient for the expected peak traffic load. In the field of telephony, quality of service was defined in the ITU standard X.902 as, quote, a set of quality requirements on the collective behavior of one or more subjects, end quote. Quality of service comprises requirements on all the aspects of a connection, such as service response time, loss, signal-to-noise ratio, crosstalk, echo, interrupts, frequency response, loudness levels, and so on. A subset of telephony QoS is grade of service, GOS requirements, which comprises aspects of a connection relating to capacity and coverage of a network, for example, guaranteed maximum blocking probability and outage probability. QoS is sometimes used as a quality measure with many alternative definitions, rather than referring to the ability to reserve resources. Quality of service sometimes refers to the level of quality of service, i.e., the guaranteed service quality. High QoS is often confused with a high level of performance or achieved service quality, for example, high bit rate, low latency, and low bit error probability. See also relation to subjective quality measures below. Contents. 1. Relation to subjective quality measures. 2. Problems. 3. Applications requiring QoS. 4. Obtaining QoS. 5. QoS mechanisms. 6. QoS priority levels. 7. QoS problems. 8. Protocols that provide quality of service. 9. QoS solutions. 10. See also. 11. Standards activity. Section 1. Relation to subjective quality measures. An alternative and disputable definition of QoS, used especially in telephony and streaming video services, is a metric that reflects or predicts the subjectively experienced quality. For example, the quality of experience, QoE, subjective business concept, the user-perceived performance, the degree of satisfaction of the user, the number of happy customers, or the mean opinion score, MOS. In this context, QoS is the cumulative effect on subscriber satisfaction of all imperfections affecting the service. This definition includes the application and the human in the assessment, and demands an appropriate weighting of diverse objective measures. Section 2. Problems. When the Internet was first deployed many years ago, it lacked the ability to provide quality of service guarantees due to limits in router computing power. It therefore ran at default QoS level, or best effort. There were 4 type of service bits and 3 precedence bits provided in each message, but they were ignored. These bits were later redefined as diff-serve code points, DSCP, and are largely honored in peered links on the modern Internet. When looking at packet-switched networks, quality of service is affected by various factors, which can be divided into human and technical factors. Human factors include stability of service, availability of service, delays, user information. Technical factors include reliability, scalability, effectiveness, maintainability, grade of service, etc. Many things can happen to packets as they travel from origin to destination, resulting in the following problems as seen from the point of view of the sender and receiver. Dropped packets. The router might fail to drop some packets if they arrive when their buffers are already full. Some, none, or all of the packets might be dropped depending on the state of the network, and it is impossible to determine what will happen in advance. The receiving application may ask for this information to be retransmitted, possibly causing severe delays in the overall transmission. Delay. It might take a long time for a packet to reach its destination because it gets held up in long queues or takes a less direct route to avoid congestion. In some cases, excessive delay can render an application, such as VoIP or online gaming, unusable. Jitter. Packets from the source will reach the destination with different delays. A packet's delay varies with its position in the queues of the routers along the path between source and destination, and this position can vary unpredictably. This variation in delay is known as jitter and can seriously affect the quality of streaming audio and/or video. Out-of-order delivery. When a connection of related packets is routed through the internet, different packets may take different routes, each resulting in a different delay. The result is that the packets arrive in a different order than they were sent. This problem requires additional protocols responsible for rearranging out-of-order packets to an isochronous state once they reach their destination. This is especially important for video and VoIP streams, where quality is dramatically affected by both latency and lack of isochronicity. Error. Sometimes packets are misdirected, or combined together, or corrupted while en route. The receiver has to detect this, and just as if the packet was dropped, ask the sender to repeat itself. Section 3. Applications requiring QoS. A defined quality of service may be required for certain types of network traffic. For example, streaming multimedia may require guaranteed throughput to ensure a minimum level of quality is maintained. IPTV, offered as a service from a service provider such as AT&T's UVerse. IP telephony, or voice over IP, VoIP, may require strict limits on jitter and delay. Video teleconferencing, VTC, requires low jitter and latency. Alarm signaling, e.g., burglar alarm. Dedicated link emulation requires both guaranteed throughput and imposes limits on maximum delay and jitter. A safety-critical application, such as remote surgery, may require a guaranteed level of availability. This is also called hard QoS. A remote system administrator may want to prioritize variable and usually small amounts of SSH traffic to ensure a responsive session even over a heavily laden link. Online games such as fast-paced real-time simulations with multiple players. Lack of QoS may produce lag. These types of services are called inelastic, meaning that they require a certain minimum level of bandwidth and a certain maximum latency to function. By contrast, elastic applications can take advantage of however much or little bandwidth is available. Bulk file transfer applications that rely on TCP are generally elastic. Section 4. Obtaining QoS. Per call. In call. In advance. When the expensive mechanisms to provide QoS is justified, network customers and providers typically enter into a contractual agreement termed a Service Level Agreement, SLA, which specifies guarantees for the ability of a network protocol to give guaranteed performance, throughput, or latency bounds based on mutually agreed measures, usually by prioritizing traffic. Reserving resources. Resources are reserved at each step on the network for the call as it is set up. An example is RSVP, Resource Reservation Protocol. Section 5. QoS Mechanisms. An alternative to complex QoS control mechanisms is to provide high-quality communication by generously over-provisioning a network so that capacity is based on peak traffic load estimates. This approach is simple and economical for networks with predictable and light traffic loads. Their performance is reasonable for many applications. This might include demanding applications that can compensate for variations in bandwidth and delay with large receive buffers, which is often possible, for example, in video streaming. Commercial VoIP services are often competitive with traditional telephone service in terms of call quality, even though QoS mechanisms are usually not in use on the user's connection to his ISP and the VoIP provider's connection to a different ISP. Under high-load conditions, however, VoIP quality degrades to cell phone quality or worse. The mathematics of packet traffic indicate that a network with QoS can handle 4 times as many calls with tight jitter requirements as one without QoS. The amount of over-provisioning and interior links required to replace QoS depends on the number of users and their traffic demands. As the Internet now services close to 1 billion users, there is little possibility that over-provisioning can eliminate the need for QoS when VoIP becomes more commonplace. For narrowband networks more typical of enterprises and local governments, however, the costs of bandwidth can be substantial, and over-provisioning is hard to justify. In these situations, 2 distinctly different philosophies were developed to engineer preferential treatment for packets which require it. Early work used the int-serve philosophy of reserving network resources. In this model, applications used the Resource Reservation Protocol, RSVP, to request and reserve resources through a network. While int-serve mechanisms do work, it was realized that in a broadband network typical of a larger service provider, core routers would be required to accept, maintain, and tear down thousands or possibly tens of thousands of reservations. It was believed that this approach would not scale with the growth of the Internet, and in any event was antithetical to the notion of designing networks so that core routers do little more than simply switch packets at the highest possible rates. The second and currently accepted approach is diff-serve, or differentiated services. In the diff-serve model, packets are marked according to the type of service they need. In response to these markings, routers and switches use various queuing strategies to tailor performance to requirements. At the IP layer, differentiated services code point DSCP markings use the 6 bits in the IP packet header. At the MAC layer, VLAN IEEE 802.1Q and IEEE 802.1D can be used to carry essentially the same information. Routers supporting diff-serve use multiple queues for packets awaiting transmission from bandwidth-constrained, e.g. wide-area interfaces. Router vendors provide different capabilities for configuring this behavior, to include the number of queues supported, the relative priorities of queues, and bandwidth reserved for each queue. In practice, when a packet must be forwarded from an interface with queuing, packets requiring low jitter, e.g. VoIP or VTC, are given priority over packets in other queues. Typically, some bandwidth is allocated by default to network control packets, e.g. ICMP and routing protocols, while best effort traffic might simply be given greater bandwidth as left over. Additional bandwidth management mechanisms may be used to further engineer performance, to include traffic shaping, rate limiting, token bucket, leaky bucket, TCP rate control, artificially adjusting TCP window size, as well as controlling the rate of ACKS being returned to the sender. Scheduling algorithms, weighted fair queuing, WFQ, class-based weighted fair queuing, weighted round robin, WRR, deficit weighted round robin, DWRR, congestion avoidance, RED, WRED, lessens the possibility of port queue buffer tail drops, and this lowers the likelihood of TCP global synchronization. Policing, marking or dropping the packet in excess of the committed traffic rate and burst size. Explicit congestion notification. Buffer tuning. As mentioned, while diff-serve is used in many sophisticated enterprise networks, it has not been widely deployed in the Internet. Internet peering arrangements are already complex, and there appears to be no enthusiasm among providers for supporting QoS across peering connections, or agreement about what policies should be supported in order to do so. One compelling example of the need for QoS on the Internet relates to this issue of congestion collapse. The Internet relies on congestion avoidance protocols as built into TCP to reduce traffic load under conditions that would otherwise lead to Internet meltdown. QoS applications such as VoIP and IPTV, because they require largely constant bit rates and low latency, cannot use TCP, and cannot otherwise reduce their traffic rate to help prevent meltdown either. QoS contracts limit traffic that can be offered to the Internet and thereby enforce traffic shaping that can prevent it from becoming overloaded. Hence, they are an indispensable part of the Internet's ability to handle a mix of real-time and non-real-time traffic without meltdown. Asynchronous Transfer Mode, ATM, network protocol has an elaborate framework to plug in QoS mechanisms of choice. Shorter data units and built-in QoS were some of the unique selling points of ATM in the telecommunications applications such as video on demand and voice over IP. Section 6. QoS priority levels. Priority level 0, traffic type, best effort. Priority level 1, traffic type, background. Priority level 2, traffic type, standard, spare. Priority level 3, traffic type, excellent load, business critical. Priority level 4, traffic type, controlled load, streaming multimedia. Priority level 5, voice and video, interactive media and voice, less than 100 millisecond latency and jitter. Priority level 6, traffic type, layer 3 network control reserved traffic, less than 10 milliseconds latency and jitter. Priority level 7, traffic type, layer 2 network control reserved traffic, lowest latency and jitter. Section 7, QoS problems. Internet 2 QoS Working Group concluded that increasing bandwidth is probably more practical than implementing QoS. Section 8, protocols that provide quality of service. Differentiated services, diffserv, frame relay, X.25, some ADSL modems, integrated services, intserv, resource reservation protocol, RSVP, RSVP-TE, asynchronous transfer mode, ATM, multi-protocol label switching, MPLS provides 8 QoS classes, IEEE 802.1p, IEEE 802.11e, IEEE 802.11p. The type of service, TOS field in the header. Home P&A home networking over coax and phone lines. Section 9, QoS solutions. The research project Muse defined a QoS concept in Phase 1, which was further worked out in another research project, Planets. The new idea of this solution is to agree on a discrete jitter value per QoS class, which is composed on network nodes, including best effort. 4 QoS classes were defined, 2 elastic and 2 inelastic. The solution has several benefits. End-to-end delay and packet loss rate can be predicted. It is easy to implement with simple scheduler and queue length given in Planets. Nodes can be easily verified for compliance. End users do not notice the difference in quality. The Muse project finally elaborated its own QoS solution, which is primarily based in the usage of traffic classes, selective CAC concept, appropriate network dimensioning. Section 10. See also. BSSGP, best effort, class of service, grade of service, GOS, mean opinion score, MOS, mobile QoS, network neutrality, quality of experience, QoE, series of tubes, streaming media, subjective video quality, tiered internet, traffic shaping, QPPB. Section 11, standards activity. Quality of service, or QoS, in the field of telephony was defined in 1994 in the ITU-T recommendation E.800. This definition is very broad, listing 6 primary components: support, operability, accessibility, retainability, integrity, and security. In 1998, the ITU published a document discussing QoS in the field of data networking, ITU-T recommendation X.641. X.641 offers a means of developing or enhancing standards related to QoS and can provide concepts and terminology that will assist in maintaining the consistency of related standards. The main QoS-related IETF RFCs are a definition of the differentiated services field, DS field, in the IPv4 and IPv6 headers, RFC 2474, and Resource Reservation Protocol, RSVP, RFC 2205. Both these are discussed above. The IETF has also published 2 RFCs giving background on QoS, RFC 2990, Next Steps for the IP QoS Architecture, and RFC 3714, IAB Concerns Regarding Congestion Control for Voice Traffic in the Internet. This concludes the reading of Quality Service.